My name is Kritika Iyer and I will be presenting our work on post-processing methods for improving MRI in painting accuracy as a part of the BraTS 2025 challenge. Deep learning for MRI reconstruction has advanced significantly, but it continues to face more challenges. Simply increasing model complexity shows limited performance gains. Large transformers or diffusion models are powerful but computationally expensive. State of the art models may reconstruct something visually convincing but may not be anatomically consistent. We are also not fully exploiting the vast repository of healthy scans. These could be leveraged to guide inpainting towards anatomically plausible results. So we asked, instead of pushing for even more complex models, could we focus on smarter post-processing of existing methods? Our approach is built on four principles. Leverage pre-trained models instead of training from scratch. Apply lightweight targeted post-processing to refine anatomical details. Combine multiple models in an ensemble for robustness and consistency. Use resource-efficient strategies so methods are deployable in clinics. Our pipeline is designed to start with outputs from leading inpainting networks. Instead of taking those outputs as final images, we introduce lightweight post-processing layer that enforces anatomical plausibility and reduces artifacts. This approach deliberately avoids retraining huge models. We get improvements by refining rather than rebuilding. We used two complementary models ranked 1 and 2 in the previous iteration of the BraTS challenge. The unit-based inpainting approach is fast and yields globally plausible reconstruction, though it tends to smooth out fine details. The conditional wavelet diffusion model excels at fine textures, but it is computationally demanding. Therefore, we combine the outputs from the complementary models using ensemble averaging to balance the strengths of UNet and the diffusion model, which are structure and detail respectively. On top of that, we apply targeted post-processing methods. This includes classical tools for morphological corrections to fix noise and other structural inconsistency. Intensity normalization to harmonize contrast across slices, reduce noise from diffusion outputs. Finally, we add a lightweight UNet as a post-processing step. We trained it by blurring healthy regions to mimic the overly smooth inpainting outputs and use the original scans as ground truth. This way, the UNet acts like a denoising model, bringing back finer details, sharpening boundaries, and cleaning up artifacts. Overall, this multi-stage pipeline improves anatomical fidelity and sharpness while still being efficient enough for clinical use. And because it's modular, we can easily adapt it to other inpainting models in the future. On visual inspection, you can see that compared to the UNet outputs, our pipeline restores sharper cortical folds and ventricle boundaries. Compared to diffusion alone, our results suppress noise while keeping details. This balance, clarity without noise, is exactly what clinicians need for reliable interpretation. We evaluated our models across metrics like MSE, SSIM, and PSNR. To ensure fairness and reproducibility, we optimized threshold and hyperparameters for our post-processing strategy using our open source BraTS ranker available on GitHub. Looking at the highlighted metrics, we can see that the post-processing improved robustness without the need for retraining any large models from scratch. To conclude, this work shows that intelligent post-processing can significantly improve MRI in painting without the need for large or more complex models. Thank you.